We are happy to have everyone here for the first lecture of the AA Summer DLAB Lecture series. And for today's lectures, we have two lecturers from AKT. AKT is a prominent structural engineering firm operating from its base in London in projects around the world. And we have together for the lecture Laura Hannigan and Edoardo Tibuzzi. So a few words to introduce our lecturers today. Laura joined in AKT in 2013 after a position in Thornton Tomasetti that has offices in both London and New York. And she holds a Golden Medal Award of Ireland, which is great, I think, from having graduated from the engineering department and having a master's degree from the University of Dublin, as well as a master's from the University of Cambridge, so in interdisciplinary design for the built environment. Her interest is lying on the applicability of a method that's called graphic statics. Graphic statics, I think we might hear more from Laura about what graphic statics is, where we can have axial structures being solved graphically in today's world of three-dimensional geometries. So her portfolio includes a lot of work, projects around London as well. A few of them are very close by, like the 125 Shaftesbury Avenue project, as well as the Rathbone Square in MEng's Rathbone Square. Now, Edoardo Tibuzzi graduated from civil engineering faculty in Rome, and he joined AKT in 2007, and now is the leading engineer for the computational unit in AKT. And his interest is based on parametric design. He has a lot of interest in parametric design, interoperable modeling, multi-scale modeling structures, and multidisciplinary design. Also, his portfolio includes various projects after he joined AKT that some of them are, you may know them, very prominent projects like the Shanghai Pavilion, 2010, Kuala Pavilion, that was the Beatbox Pavilion called in London 2012 Olympic Games, as well as Birmingham's New Street Station and Bloomberg's London headquarters. Edoardo is also a teaching fellow in various schools like the KTH in Stockholm, has led various workshops at Tor Vergata University in Rome, UCL, Colgate University, and Royal College of Arts. He is also a co-author of Design Engineering Refocused, recently published in AD Smart 03. I think I covered all of it, I hope. If I missed anything, please. So without any further delay, I would like to invite our lecturers. Please help me welcome them for the lecture.
Thanks very much. Even that is going to be hard to follow. So thanks for having us here. It's really nice to be here, and yeah, we're just really looking forward to talk to you guys and hear what you guys have to say as well at the end. Before diving into some of the project examples, I wanted to touch on really the fundamentals of what we do. As everyone here is everyone here an architect? Do we have engineers here too? Engineers? Great, well you guys, we'll skip over this then. But fundamentally, when we approach problems, which we're going to get onto from the computational side, still the fundamental principles of engineering we'll always try and stay through to. So when we're talking about form, back to basics, right? We're designing structures for wind, gravity, other lateral loads. We've got seismic loads and anything else that can throw it. And within those structures, you're going to have, you know, elements in compression, tension. We're designing for stability, bending, buckling, everything in between. So an element in a structure, every element is there for a very specific purpose and performing a very specific function. It's always interesting when you see the end product, whether the structural form has followed the aesthetic form, or the aesthetic form has followed the structural form, or they have in some way waltzed together to get an end product where you're not actually quite sure, which usually results in the best quality project. So looking at complex forms can be interesting because sometimes it can be difficult to know whether it is aesthetically driven, structurally driven. And even in what can seem like potentially complex forms, you should still be able to find say a pure structural logic, or that's what we would like. So if you don't believe me, you can believe nature, of course, where you can see primary ribs with more material on the upper part of the wing, where greater stiffness is needed. And then the primary ribs drop off to less material, where more flexibility is needed in the lower part of the wing. And that is obviously seen in, you know, it seems obvious to us, but a vulture's bone wing, which is naturally formed with a Warren truss. So you've got an optimum amount of material and weight. Or in bamboo, which grows naturally with denser material on the outside, so it is perfectly designed as a cantilever, resisting wind loading, which is pretty much all it needs to resist, it and its own self-weight. So these examples are from Darcy Thompson. I'm sure you guys know it, on growth and form. And he was one of the first to look at mathematics as applied to biology. So what's interesting is that it touches on not only structure, but also geometry. You've got the example of the spiral of Archimedes, where a spiral continues with an equal width. In nature, you've also got the equiangular spiral. It's not just in nature, but you can see examples of it in shells, where the actual creature inside, I'm not going to attempt the Latin, by the way, but if anybody wants to, go for it, grows. Its shape doesn't change, but its size increases. And so the spiral increases at a constant rate continuously, which is really quite nice. So it's allowing the creature to grow in size while maintaining it, but it's just a simplicity that is quite pure, essentially, while maintaining the form. It also describes the path an insect follows as it heads towards a light, because its eyes don't look straight on, so it's constantly adjusting its angle. Sometimes in structures it can be difficult to discern where the form has come about, or also why the material is there, which you can make your own opinion about that as well. But we would always try and, from the start of a project, find that pure repetition and logic and simplicity, which can seem, you know, complex at the end product, but and Ed will be able to show some product examples of that, where fundamentally it's based on pure principles. So how do we design? You know, back in the day, it was, back in the day, I say that as if it was when I was young, but I'm not that old. This is scale models, which are used by Gaudi with loads, weights, hanging chains for form finding, which are obviously really intuitive. And what's interesting, well, we'll see why it's interesting. Graphic statics is a method mentioned and touched on there as well, where the structures, axial structures, are solved purely based on their geometry. So lines are drawn essentially parallel to the members. So if you think of an axial force, drawing the line parallel to the member, you're drawing the axial force line. And you can draw use proportional geometry to map out your forces in your structure just based on geometry. So you don't need to go down the good old calculus route, which we use these days. It can be limited in its solution in that it is axial structures only. But yeah, part of what I was looking at is the really interesting full circle that we've come from initially designing graphically and very much using models and graphic solutions. Kind of come full circle now, back around to using obviously really graphical programs. So with computing, we went down the calculus route because obviously they're so powerful in computing multiple things at a rapid rate. That's the equation for, I think it's like point location for the British Museum, or so I was told by who provided it to me via Chris Williams, who worked on that. And we ended up in a position then where we're using finite element models, and this isn't a new thing because Whitfield Science Centre was constructed like 12 years ago. So obviously it's the same kind of models and stuff that are used in different industries. But what's different now is that whereas 12 years ago that would have taken days to compute a single iteration, and a lot of more handwritten code. Now, obviously, as you're all aware, you could iterate that in multiple iterations, that more in a matter of minutes. And how we do that and react to that is through programs such as Rhino and Grasshopper, and moving it into analysis packages, which we use, such as Sophistic and SAP and Robot. So we have come full circle in that previously it was analysis and physical model and getting reactive results. And that fell away for a while with computing. But now we're back to it with being able to analyze and have an analytical model and get instant feedback. So this circular approach is really reactive. So ways that we have used that, not only through fabrication and production, which you'll see later on as well, but through design. So, example here is where we were looking at a facade, and we're going to use all the facade elements as structural elements. It's nice to have columns line up sometimes, but they don't always have to. But maybe I shouldn't say that. So what we wanted, we knew that the facade was obviously going to move a lot, right? If we get a first iteration, of course, windows are going to change, apartment layouts are going to change, and we wanted to give the architect as much flexibility as possible. So we kind of set up an initial, very, very crude design script with allowing them to move the panels around wherever they want, essentially, with certain rules. And it was directly linked to our analysis model, where we're checking the shear transfer basically between column elements, which would transfer through the slab. So instead of having one iteration and coming back, we're able to inform the design rather than just react to it. So we're able to tell them what an efficient design is. And quote which spotted yesterday, I'll be called out on this if any of you know it. Quotes are cheesy, but it's an interesting one with how it talks about how when technology reaches its real fulfillment, it transcends into architecture. Which is true, because when you think back to the days of skyscrapers, it was when, iron ore came about that they obviously started being a lot less solid. You went from solid masonry to being able to open up facades with curtain walling then following. And so the technology inherently will influence the architecture and the structural leap. So now that we're able to analyze models so quickly, we're able to inform it at potentially a more rapid rate. And I say you might have called me out on it because it's a quote from the 1950s, which is interesting as well, because I always like the reminder that obviously interesting forms have been around, or terms like hyperbolic, I even messed it up. I'll let you read it instead. Paraboloids have been around, but it's how we go about it, and it's how we design it and how we interpret that. at a much more rapid speed, and the fabrication as well, which you'll be able to see much more streamlined than potentially Candela had to go through when you see images of his formwork. So at that point, Ed's gonna pick up on explaining more of the computational side and with project examples as well.
Yeah, so actually, as Lara was mentioning, we're going to look at some examples on how we apply this sort of techniques. But before that, I would just want to cover a little bit of where we're coming from as structural engineers. Obviously, we are almost in the middle of the process of designing a project or a building or an installation. So, and we get a lot of inputs from all different practice, inputs from architecture, inputs from cost consultants, from clients, and so on. So, in this sort of universe of data and inputs, we're trying to sort of create and entangle this structural model. So by assessing all this data and information, we're trying to define our final structure. So, and code and scripting is coming a lot more into helping us in this sense. This is actually a graph of AKT, the average age, and you can see that most of us is generation Y. Which inherently we are in this generation. I say we, but actually not. I'm not in the Y. But there's a lot more interest into coding. I mean, I got a 2-year-old son, and he's actually have a small book of coding, and I'm pretty sure he's going to be able to probably do an if statement before he's going to actually be able to write his name. So, I mean, code is important, and there's a lot of actually different languages can help us into sort of speed up and automate processes. And we actually, as a computational team, started to sort of question ourselves, how can we use code to actually arrange our software and our process into one unique system and workflow? Why do we want to do that? Well, because I think we understood that the process of creating something has to go through different loops. And actually, this is one of my old friends, is a mathematician in Ljubljana. Actually, once explained me the difference between analysis and synthesis. And it's quite interesting because when you're creating something, you can actually do it through analysis. So you go into the past, you just start from an hypothetical solution, you sort of kind of assess what's been done already, and then you combine these things and you get through the solution. Or, and this is a process of understanding. Or you can actually go the other way around. You can just actually look at the future without knowing where you're going to go. You can just combine your data that is available to you at that point in time, synthesize them, and create your sort of final product. And that's a process actually of creation. So that's got a lot of similarities in what we do. And this is actually a process that iterates around, and you never know in the process of your design where you're analyzing something or where you're synthesizing. But actually, as long as you're doing this loop, you'll get to your end process. And if we look by using the tools that we are available at the moment, in our industry, we have a sort of a linear process where the client gets instruct us with a with a project. Architects are usually very in the early stages creating the sort of concept of it. The structural engineers and all the other guys are trying to help to make it stand or work or perform and so on. And then you get the build process. But what if we come up with a series of tools that integrates all these different aspects into one single workflow, which is not BIM, by the way, to help us and all the other designers creating a much more performative building, and that actually mimics the process of creation and understanding, so analysis and synthesis again. So all of this to say that we actually started to look at interoperability to actually achieve this process, and we kind of put up together a solution that we call React, which is a sort of an interoperable model that helps us connecting the different softwares and the different processes that we use during the design. This is a screenshot that is managed in Rhino Grasshopper, and it helps converting all the different data that we're using into the different softwares that we use in the company. So whether it's a structural analysis software, a production software, or an environmental software, we have the connection to it, and we just deal with one unique model. That allows us to just go through parametric design, structural analysis, and BIM at the same time. So I'm going to show you a few examples of what I'm trying to say here and how we apply this sort of workflow in real life. This was an early stage involvement we had in a sort of almost a master plan insertion in the States, Mountain View for Google. So obviously, it's nothing new in terms of concept, but actually it was the first time they tried to apply it to this scale. And our sort of involvement was in different sides of it, but I'm going to focus on the generation of the dome. Again, if you see, this was like a 4 months involvement, or I think 4 or 5 months. And if you see from the start to the end, the amount of iteration that we had to go through, different materials, different shapes, different forms, different structure solutions, it was simply not going to be possible without having like a unique workflow that allowed us to go through these things. And when I'm just looking only at the form finding process, again, as Laura showed us, in the past was done through physical modeling and then, generation, the final sort of source. In this case, we actually applied, computational tools to let us understand how this shape would deform under their own self-weight, under the actual wind loading, under the other sort of loading condition, but also trying to be able to manipulate the stresses within those sort of patches creating the cable net, in this case, and to be able to modify the various stiffness within all these elements to create the desired form. So we set up again this approach in a computational manner, where we've been able to control every single parameters of the sort of stiffness of the cables, and then we just relax the model. So we kind of been able to assess also the geometric properties, but also the effect of the structural properties onto the architectural parameters. So in this case, we've been able to map the warp of a glazing panel, which was resting on the cables, in real time, and be able to sort of vary the stiffness to reduce the warp in the worst conditions. Again, so these sort of ways of approaching the problem give the designer the flexibility of informing the rest of the team about really important issues. For example, in this case, we went a step further and we assessed the effects of the seismic actions on the planarity of the panels again. So we did perform a time history analysis to understand the displacements due to the seismic actions, and we mapped them back on the geometry again to assess which of the options in terms of geometry was performing better under a seismic event. But not only that, we have the capability nowadays then to inform a 3D model with all this data, so we can map a series of information on top of it and communicate it to the design team much quicker. So again, as I said, this allows us to span between different options and allows the designer to focus on more important issue rather than make the system work, or maybe to design more into sort of detail specific parts of the project and take care a little bit more on the actual sort of design of those parts, basically. So as I said, various iteration have been pushed through this project in different materials, and every time we use the same sort of engine, the same backbone for the analysis. Couple of images and a couple of look at the future as well. So as long as we save some time, we can also look at what maybe the future reserves us, and be able to kind of space out a little bit with imagination. Another example, this actually is going to look a little bit more into detail on the workflow and how we set it up with the rest of the team. So this was the Serpentine Pavilion last year, not this year, with BIG in London. And there were several sort of challenges in this project. I mean, one was the team. We had, a team scattered around, and it was very, very, sort of short process as well. So in a way, the other challenge was the time. I mean, if I'm comparing the Serpentine program with another very short program on a building we've designed and delivered in Bournemouth, you can see that the actual Serpentine was delivered in half the time, only 28 weeks, which is very, very compressed from inception to the end. So again, and another challenge was the location. All the team was sort of scattered around Europe, and there were these sort of two channels, the design route happening between us and BIG, and the construction route happening between Fiberline, which were the composite material provider, and Stage 1, who assembled it. So challenges that actually sort of had an impact on the use of the tools that we actually in the end been using. So the design was very quickly sort of resolved. I think it took very, very quick shot at picking up the final shape. And the recipe is very easy. It's 1802 GFRP boxes assembled with many aluminum connectors bolted together, to form this sort of stacked system. The geometry was very, very simple. There is two sinusoidal curves and an horizontal line lofted, creating these two sort of walls. And the component, again, was made out of GFRP, single extrusion, glued together with GFRP angles, and then stuck together with aluminum extrusion bolted together. So very, very simple. Complexity here was in the setting out. To create this sort of system, we had to sort of play quite a lot with the different spacing of those boxes. Material is innovative, hasn't been used in this scale before. Is a GFRP extrusion, so there's got fiberglasses extruded into a different sort of shapes. This shows how the actual fabricator is implemented the process for actually this pavilion. So they do all sorts of profiles, but they've did this single extrusion customized for the pavilion itself. It's translucent depending on the size or the thickness of the material, and that was why it was chosen. The architects wanted this sort of translucent effect. Structurally, we sort of looked a lot into sort of the arrangement of the boxes, but basically how to resolve the push-pull forces within the stacked system. So to be able to control the structural behavior and to be able to feed it back to the architects, we set up this workflow that allowed us to sort of analyze quite quickly the structural performance of the building and just feed it back to the architects as quick as possible. And we also sort of tried to visualize the information that we were finding out of our analysis in a sort of a simple and visual way, so the architect would know exactly where some boxes would fail and what to do in that case, maybe increasing or decreasing the length. So we use the system to communicate back and forth with the team and to allow them to actually progress with the design quickly. But also we've been issuing all our discoveries in the digital form. So we inform the box thickness, for example, and the other sort of parameters. And this is actually a screenshot of how the project looked like in the end. We had a initial part where it was shared with the architects and defined the geometry. And then we used that single geometry to create our global and local FEA models. And we combined the information gathered from the structural performance into one database that was structured in one-to-one with the actual boxes. So every box had a set of parameters. And then we've been able to transfer this into the production information. So every time we would assess and modify the input geometry, we could potentially just push the button and produce the construction information. What is important also for this sort of project to see the scale that we can actually, assess with these actually workflows. We can actually have a look at a global scale and a local scale, which actually gives us a lot more sureness on how the model behaves. And in this case, it was very useful because we had to sort of, at the same time that we were designing the project, we had also to perform some physical testing in order to verify our models. So we were quite lucky to have this, and that doesn't happen very often. So, and we've been able to sort of compare our local model, structure model to the actual test model, and you can see that the trend kind of was reassuring, and it's very, very interesting the fact that we could do this in a parallel sort of session. What I really like of this sort of approach is that you never know, because you have a lot more control on your, sort of geometry control, analysis control, you never know what your sort of design would take shape and where it's going to end. So because we had so much more interaction with the architects and we could sort of go through these different options, we could actually implement and improve the design a lot further than we would have been able to do it without these tools. And I'm just going to breeze through this. And again, it's quite good and handy when you get to the final part of the process, when you get into the production phase, to have a system where you can actually extract your information quite quickly, but also documenting it, in a very sensible way. The contractor loved us in this sense because we just managed to sort of summarize the properties of every single boxes and how those boxes would be set out against each other with a series of very simple diagrams and some spreadsheets. So again, if this would have been done in a sort of more traditional way, it would have taken only ages to produce this information in this sort of short term, and that wouldn't have been practically possible. And then just a very quick sort of breeze through how this then got built. It was fabricated in Denmark. Then it was the aluminum boxes were sort of extrusion were pre-drilled again in Denmark, and then it was assembled in stage 1 premises and built, in the last 2 weeks, I think, or 2-3 weeks. And these are some shots of the structure coming up. Just gonna quickly go through. I think I've got a video in the end that can show you. It's been dismantled, but it's going to be reassembled in Vancouver, which is very good. It allows us again to test, the sort of longevity of the project. But also we did a sort of in the end, to capture what was the scope of the project, we did a short drone movie, which is quite nice. And this will actually show you also the translucency of the material, which was quite nice in the end. I don't know how many of you have been to see this, but yeah, I found it very interesting as a final design. This sort of ambivalent kind of geometry, open from one side and closed from the others. It was very beautiful. So anyway, I'm gonna just skip through this because I don't think we have a lot of time, but similar concept applied on a different sort of project, different scale, different use. So this is a project in Hudson Yards with Hedwig Studio. It's sort of a gigantic staircase which is going to be installed in the redevelopment of the Hudson Yards. Again, started from a very, very simple concept, wrapping around a sort of sheet of paper and then kind of setting out this up and down staircase along it. So very simple rule on a 2D sort of configuration. But then when you go and sort of start to develop the system and think about how it's going to become a 3D sort of extrusion, you start to see the complexities in terms of geometry. So again, the ability of actually having a control on the geometry from the beginning and have a response in the background in terms of structural performance allowed us to really push the limits on this. It all kind of structurally works as a middle layer that provides the structural performance, and then an inner and outer layer, a set of cantilevering ramps from the actual backbone of the structure. And we set it up with a very series of simple rules, starting from the center point of the landings. The parametric model will control the width of the landings, the slope of the stair, and so on and so forth. So again, the ability of controlling not only the inner layer of the structure, but also the depth. So being able to vary these parameters to meet building regulations and architectural aspirations and so on. And it's been quite a lot in terms of design engineering, this piece, because it's an uncommon structure, and it has to go through a different series of checks that are not very usually common for a building, and especially in terms of vibration being a staircase. So we had to go, and also fabrication, it's kind of a very twisted sort of geometry. So again, the control on these parameters was fundamental and allowed us to really go into detail on how to set up the global analysis models and extract the information that we required, but also to model the structure up to the very detail on the joints. And then sort of feedback the information that we required also to assess the structure in the dynamic configuration. It uses some technologies to reduce the vibration, such as tune mass dampers. So it's a very complex sort of structure, if you want. And every time the shape would define and be changed, this information would have to be reassessed. So, but also in terms of production, if you can think on how it's fairly simple to set up a beam in space, but if you want to set up a structure like that, it's quite complex. So again, being able to extract the parameters and being able to schedule them out to actually give the contractor, a good information was fundamental, and that's we've sort of managed to achieve that using those tools, and without them we wouldn't have been able to. So it's a bit of a construction sort of arrangement, and it's actually it's being fabricated and actually erected at the moment. So it was quite interesting as well to find the right contractor to be able to follow our requirements and being able to sort of produce what we've created or designed together with the architects in such a meticulous way and down to the detail. So it's pretty impressive piece of engineering in a way, because it's all sort of structural steel welded together. And the scale is really impressive. So from big to small, but the complexity here was the fact that this bridge was a movable structure. So the Merchant Square Bridge, if you haven't been, just go down Paddington, it's quite nice. And again, in here, the sort of trick was to actually implement the movable sort of mechanism into the structural design and assess the impact that, in this case, mainly wind would have on the mechanism. And trying to define the optimal position then of the piston and the pivot. So all of those things have a massive impact on the structure, because it allows us, if we calibrate the position in the right way, we can allow to actually reduce the material. And that's what we actually did by sort of importing into the parametric model the structural properties, the wind effects, and use it to actually position the pivot and the piston relative to it in the most optimal way. Again, a very small exercise, but the benefit that we got out into actually inserting this parameters into the analysis and into the geometry, made a big impact on the final sort of thickness of those blades. Again, this was made by fabricated steel section, but again, we've managed to reduce the thickness of those quite dramatically using those tools. The Bloomberg vortex for us was one of the few different parts that we actually been involved designing the overall Bloomberg headquarters. I chose it because to me it's quite a special project because it uses a very simple technology and material, which is timber, but in quite an elegant way. Again, the project was in collaboration with Foster's and Partners, and you know where Bloomberg is. It was quite a challenging project from a lot of different perspectives, but it was also like quite a discovery. I think it's been one of the biggest archaeological finding in Northern Europe. It's got like special parts like the vortex and the ramp, which constitutes like the knowledge factory sort of aspect to it. But it's also got a big infrastructure sort of works beneath. So it's very, very interesting project overall. The vortex was conceived as a entrance bit where sort of as a Bloomberg kind of company ethos, mixing up the workers and then elevate them through the ramp through the rest of the building. So it's got quite an interesting shape, and the brief was to kind of create this three leaves resting on each other, sort of a very curvilinear shape, and to clad them with an very nice acoustic panel finish. So when we actually internally debated on which way was the best to approach, we sort of had this kind of dual aspect. Shall we go to and design a steel structure which is going to have to resolve the complexity into the brackets of the panels, or shall we go for a traditional system where we can create a setting out surface where the panels can be just laid on top? And because we had some experience in doing that in a previous project, the BMW Pavilion, we thought that the second one was the actual better way. Timber, great material, very easy to sort of to shape and model in a way a bit, even inexpensive if you compare to other technologies. And the thing that I like of timber is that allows you to, in this configuration, allows you to kind of define the material and use it in the areas where you need it the most. So when we just actually thought about the vortex, we thought, let's try to do it in this way. And we had to work in collaboration with Foster's, and that was a very interesting experience because actually they have also a computational team, and they really went kind of in a pure approach in this, and defining the actual geometry of the vortex and on the ramp. They define it with a mathematical equation, the apotocroid curve, actually one of the configuration possible of this. And then we thought, okay, let's define a common workflow together to being able to start from that equation and deliver the project in the end. And the beauty of this is that it was one of the first approaches that was successful up until the end, which we kind of take a lot of pride in because it was a journey in a way with Foster's. So the concept is here that we are rationalizing that doubly curved surface into a rule surface by just inclining the joist accordingly to find these conical surfaces. Therefore, we are kind of providing a very simple setting out system, just providing 2 points at the start and the end of the joist, and the ply in between those joists will form the actual shape, which will be then the setting out for these cladding panels. So as you can see, even from the detail, it's a very, very simple system where you have vertical sort of long joist connecting throughout the other direction with noggings. Everything is bolted together, and then the ply is actually applied on top of it using nails and glue, staggering 2 different layers in the walls. So it's a very, very simple system to fabricate and to install. Initially, we thought about installing this series of long panels Then we reviewed this one when we went on site. But basically, it's a very, very simple structure. It relies on a reciprocal connection on top, and then it's supported at the ground, so it's self-supporting at the ground. So the only structural connection, if you want, is those three series of trusses linking the lips of those walls together. We had the extreme luck to have the chance of doing a mock-up on it, which is always great, informs the process quite a lot. And during the mock-up, we highlighted some different structural solutions. And then simply the timber was cut in Switzerland, shipped to the UK, where it was assembled by the contractor, following a fabrication set of drawings. This was the assembly, so where the joists had the splice, we provided a structural plate. And then the noggins would be sort of inserted in a sort of a ladder fashion, bolted together, and then those panels would be pre-assembled and again bolted together on site. The ply will come on top on site again, forming this very smooth surface. So this is how it looked like in real life. This is the skeleton with the actual pre-assembled cassette ready to go on top. Then the ply, as I said, it was actually scheduled out, glued, and then staggered in two different layers, as you can see in these kind of shots. So very, very simple. And then this is the final sort of smooth surface where they kind of lay down the top acoustic panels on top. Internally, it was insulated to provide environmental sort of properties. And that's it. I think this was taken like 4 or 5 weeks ago, where they were starting just putting up the cladding. So it's funny how big projects are always informed by small projects. So the Vortex for us was informed by this small installation we did with the Akisa Hirata and the Architecture Foundation. This was the only piece of information we ever received from the architects. It was a real model and a plan showing their intention. So we had to sort of find a quick way to sort of find the optimal kind of configuration for the geometry ourselves. So we kind of thought, how do you sort of feed a single kind of ribbon of material inside a room, and what's going to happen if you do that and relax it? So we use this process, like again, from finding to kind of create the most optimal shape for the installation. And then we tested for the first time the approach that we kind of applied to the Vortex. So again, a stress skin solution. And this was the final result. Again, very, very interesting. With an inexpensive material, you can create sometimes quite interesting forms. I think this is the last project. Just tell me if I'm going too far. Do we have time? So I'll put this because this was the sort of one of the most complex projects in terms of location, size, and also clearly architecture. And this is the Grand Theatre of Brewery in Rabat. We saw it. The complexity here was trying to define a way to collaborate again with the architects that would allow us to sort of engineer this complex shape. And we started from very, very first principles. We extracted the curves defining the shape of the architecture and defined the structural grid. And then with that, kind of start to create the backbone or the skeleton of those structural ribs along the facade. And then bit by bit, we added sort of the complexity, going through the edge beams, the internal walls, and the concrete. So again, this was kind of set up in a parametric version because every single offset of the structure, every single element of the building was kind of modified up until the end. And again, it's a very good example on how, without these tools and without this process, we wouldn't be able to achieve the final result that we have here. As Laura was mentioning, Fino was one of the first examples. I think Fino went through a lot less iteration in comparison to this. So it's a very interesting aspect. And again, very easy way of kind of scheduling out information in this case, getting the sort of setting out information straight back from the actual analytical model and scheduling out in a sort of a simple way, a series of sections around the building. Yeah. So let's just going through this. And also to set out the actual facade that actually creates this curvilinear sort of shape. Again, these shells in between the main structural ribs were all sort of automatically exported from the model and scheduled out, sectioned and elevated automatically from the final model. So this process works in different scales. What I'm trying to say is very flexible in a way. And these are some images from the site actually a few months ago. The very last bit I want to go through is the application of instead of another aspect, so the environmental side of it, and how we're actually trying to assess and use a different aspect, a different data that we can extract from the environment, in this case wind, solar and thermal properties, and use them in the design process to inform maybe the shape of the building or the impact that a specific building has got on the built environment. And this can be done in different scales, at the master plan scale, at the building scale, or at an envelope scale. And the approach so far has been to do it using wind tunnel testing facilities, which is usually quite a long-winded process. It requires quite a lot of investment from the client side. So we just had a look at trying to see if it's possible to do it in a digital environment. So we've been sort of researching together with a Swedish company, Tyrians, and a small UK-based consultancy, Gas Dynamics. We put up together this digital environment where we can assess bioclimatic impact on a building, in this case wind comfort and thermal and solar comfort. So we just run the CFD calculation into our own design model, so we can create all the boundary conditions and all the sort of properties into our 3D environment, run the calculation, and then extract the sort of information back into our model to visualize the effect of the wind onto pedestrian wind comfort in this case. So again, it's a very useful tool. We use it quite a lot in terms of planning applications at the moment to inform the impact of an existing building or of a proposed building on the built environment. And we've been also looking at different aspects like solar radiation inputs and how to sort of extract the information of, in terms of Hardy shading masks or sky view factor maps, shortwave radiation. And then we can have a sort of an envelope of the yearly sum of solar radiation mapped back on the side, for example. We did in the past also look into glare, for example. This was a study done in Birmingham New Street, where the impact of glaring in relationship to the buses going around the site of the station, but also on the tracks, was sort of fundamental. So the angle of those reflective panels of the cladding was informed by the study. But also thermal comfort. In thermal comfort, it's an energy balance of all sort of different aspects. You've got a direct shortwave radiation, the shortwave reflected, the long wave emission, and all of the parameters combined into one to kind of really get and extract the surface temperature of a building. We also sort of look into like how to map these values into a universal comfort index. So we use this UTCI comfort building index and being able to map that implication on our sort of environment to actually really assess what perception the human scale would have in that sense. So, in a way, I hope that we sort of managed to with a little bit of delay in terms of time, give you an overview of what it means to apply the tools, apply those techniques into the real environment, and how important it is to actually just being able to control your design, not only architecturally, but also trying to feed the data as much as you can into your design process. Thank you.
So my question is, how do you see, I enjoyed the fact that you mentioned that the tools that we have and the way we can use them to control our design is very, it's developing and it's becoming quite practical at this point with geometries that are very complex. What do you think about the fact of changes? So with all the various deadlines and the constant, let's say, alterations, the complexity together with the development of those tools, what are your thoughts about it? Do you see something as equally complex to achieve, or do you think it's actually becoming more and more facilitating?
It's an interesting question because actually I think you're right. It depends on the project, So in a project like the Rabat setup, it allowed us to, those tools allowed us to really being able to reflect those changes that were coming from maybe the client or the architect or from one of our solutions. In a way, it increases the layer of possibility and allows us to sort of react to those changes quickly. But sometimes, it's the other way around. It just gives too much flexibility, and people rely on this speed too much, and so I think there's an aspect to it as well that is it's not only the speed and the ability of actually reacting to those changes, but also the detail that you can go in terms of analysis. That is actually a benefit. If you want to expand Laura on this.
I think I agree. It's about holding on to the creativity that you impart to it as well. So when you can output 50 different, potentially what could be classified as optimum solutions, it always will need someone still to decide which one is, or maybe there's 100 solutions which are within 10% of that solution, and retaining the human creativity to it is obviously really, really important to inform that, to make sure that you don't end up with flicking through 200 options.
Mm-hmm. Yeah. All right, has anyone any questions? I think it was also, I don't know about the people who are in Summer DLAB. A lot of the topics that we touched upon are very, very relevant, and I hope this lecture was very insightful for everyone here, because we're going to go in our own kind of way and tackle this aspect. So I want to thank you very much. It was very informative. And again, there's a question. All right.
Me as a young architect, I find it quite interesting to see people working on these projects, and this is more of a personal question. What got you to this point? What is it that you're working in projects with Zaha Hadid and Foster's and Partners? What is it?
Why are you doing it?
I think this is a question that everyone that works in this industry sort of asks, why are we? I think the question is, why are we doing these things? No, but I think I mean, I think we are quite lucky to be able to, collaborate with all these people. But it's not only who you're collaborating to. Sometimes you can find a very, very challenging problem in a very small installation with a very unknown architect, and the effect that has, the impact that has on actually how you design even bigger sort of challenges is massive. So I don't know if I'm answering to your question, but I think it's more, trying to find the right challenges and the right projects every time and try to sort of assess them as you go and,
Yeah, I think how we end up, or where we are, or what we're doing as well, there's a really good, kind of group of people as well within the office, and they've somehow managed to create that, which kind of drives itself on. And the office as well seems to try and ensure that every project is quite unusual and bespoke, because they know actually that's what people want to work on. As engineers, we want to have a challenge. And with every challenge you solve, it drives on to a completely other one. So it is a driving force. Maybe you get the right people in place first, and then the first one comes along, and then it just self-perpetuates, because you want another challenge the next time, or an even harder one the next time, and they always do seem to arrive. I don't know how.
I have a question. I want to pick up on this really interesting diagram you showed about analysis and synthesis. So, it's about, we work with data, we analyze things, and then at some point, as a future, let's say, projection, we have to do a synthesis. And, we can see that, like, nowadays with, all this, with the increase of, let's say, resolution in the data and the types of data we work with, synthesis also becomes a very kind of complex process, I assume. And, obviously there are many offices taking part, like with all your collaborations you showed, and like operating in different countries and being part of this process at different stages. So I'm wondering how that synthesis kind of takes place at the very end, and where do you see yourself as an office being situated in that process of synthesis?
Yeah, it's a very interesting question, actually. So the first part, I think, with the interoperability approach, we're trying really to sort of overcome that, because the complexity when you're receiving this immense amount of data, and to make sense of it, but also to use it appropriately and to be able to filter it to your needs is fundamental. So, without scripting and coding, this process wouldn't probably be possible. You would end up sort of using an approximation of that data or your interpretation of it without even being able to instead use it, in the right scale. Example, when you design maybe a complex steelwork structure, and you're sort of assessing, specific impact of some loading onto it, even internally, I'm saying, right? Sometimes if you think you need to stiffen that a particular place in that structure, you would do it as a generic rule, and that would have a massive impact on the, on the configuration of the steel. Instead, being able to forensically understand that model much more would allow you to interpret the data better and to remove that generic rule and to use the actual property that you need to inform the configuration of the steel. And when you expand it to an external company, when you receive, environmental information or, other sort of properties, being able to implement them into these workflows is the actual real benefit. So we are doing it computationally, so we're actually try to set up the project in a way that we can implement this data in. And I think that's it's proven to be the best approach for this kind of projects, actually.
I have a question. My question relates a bit to like the future. and like you showed the diagram of each of the programs, Revit, and all of the softwares we use, and you try to find a way to like combine all of them. For me, I want to know, like from the point of view of an engineer, what do you think of the fields that try to innovate in a more simplified way the construction side of buildings, like research labs of self-assembly or this kind of researches?
So in terms of, the actual constructing of buildings, I think that's where you can see most of the immediate future innovation happening and where it almost needs to and should happen. So some contractors are investing a lot of money into researching, and I think I've noticed a lot more contractors actually teaming up with universities as well directly, which is unusual. Well, I think unusual, because what we're doing now needs to be caught up with. I've seen something, so even with virtual reality, being able to either design through virtual reality or to show prospective clients a finished building, or even to interrogate the structure and design, imagine bringing that to site. And I've seen some things where on site, as people are building, they're able to do augmented reality, overlay, say even the reinforcement layout. So you can look on site and you can do an augmented reality and see what you're building in front of you. But even then, how reactive we are now to design, I'd be interested to see what comes out with how can construction be reactive. So society is, company lifespans have gone from whatever it is, I don't know the actual figures, but I'll make some up, something like 50-year average company lifespan now to, I think it's 4 or 5 years. Our design is incredibly reactive, but if you decide to build a building, it can take years through concept and planning and then construction. And from a personal point of view, I'm interested to find out, maybe you guys can answer, how can that change? And that surely will need to change because society and design has changed. So what if in 2 years' time you decide you've changed your mind about the building, or actually its use is already defunct? So yeah, there is a lot going on in construction. There's, I'm sure you've seen it's old now, but drones being used to place building blocks or to do 3D printed concrete or different ways. It's hard to see what will stick and what will be implemented, but it's good to see that there's so much research happening into how to construct better, quicker, more reactive. I'm not sure if that...
So just the 2 examples he showed us, his work we do in the Hudson Yards, New York, that one, and the Foster partners, they both do stairs and they do a lot of expression, but at the same time, stairs, people movement from vertically become structure themselves. So it's kind of 2 tendency go to 2 extremes, and you guys doing things about standardize all the things and do statistic analysis about that. So how did you, as playing this role in the whole process, how did you balance out the 2 tendencies to go to the extremes right now?
It's very. I think that's part of our daily routine is to find a balance in things, and it's a question of actually trying to. It's a very hard question actually. Well, the Hudson Yard was a very interesting project because of the scale, I think. So trying to kind of control that scale and still being able to deliver the performance that you needed was a challenge. In the Bloomberg, I think it was more like sort of more like a structural problem in terms of the ramp, in that case, not the vortex, but the one above, sort of was envisaged without any support. So we were trying to go against gravity in that sense. So to lift people up, but trying still not to support this structure anywhere. And in the end, we sort of managed to get very close to it. So yeah, it's, I think this connects a little bit to the question before. I think the beauty of our industry is that every single product that we deliver has got different outcome. And if you look at the future, you know, AI, machine learning, you can put everything you want in there, but the bottom line is that the outcome will always be different. So, and that's the beauty of it. I think you can generalize things, you can find resources and tools that actually allow you to design and think quicker or to get your answer quicker. But the bottom line is that the thing that you're gonna make in the end is not gonna look anything similar to the thing next to it, which is actually what distinguishes our industry from all the other one. And that's why those techniques are also sort of struggling to permeate. These things were applied in automotive and other industries for ages, and that's because you do one product and you repeat it forever, you know. But the dualism of our industry that goes back into the tradition and trying to make something that stays there forever. Therefore, you know, the structure needs to stay there. And instead, also the fact that instead you want to maybe do something that changes in 2 years' time. So you want to do a building that is flexible, that is reconfigurable. That dualism is something that really fascinates me, and that's sort of driving the industry and those processes, I think.
Should I stand up again, or no? Okay. Well, I would like again to thank for the lecture today. It was very informative again. Thank you for coming, and thank you for being here to enjoy the lecture with us. Make sure you join us for the next one. We have a couple of lectures following up with the Summer DLAB. So, once again, thank you.